Okay, well, let's spend some time talking about Chapter 7 in our textbook. And some of this stuff is going to be repeat. I mean, this book seems to kind of repeat certain things quite a bit. But we've talked quite a bit already about different types of linear energy transfer, like how radiation can be referred to as, photons. But the big thing that we're going to be looking at is differentiate between these different levels of biologic damage that occur within living systems, as well as talk about this target theory. So, again, we will try to differentiate between physical, chemical, and biological factors that influence a cellular response to radiation exposure. Okay? We'll also talk about DNA damage and the types of categories of cellular response. So it's important for us to know how the cell will respond to the DNA damage. We'll get a little bit more in depth with the law of Bergonié and Tribondeau, and we'll start to draw some cellular survival curves and discuss factors affecting the cellular sensitivity. So it's very important for us to be able to think about how radiation interacts with different types of cells. So as we mentioned, DNA is going to be our primary molecule of concern. And as we were looking at the mitotic and meiosis type processes, one of the things that we focused on was how these DNA processes were occurring within mitosis and meiosis, because, again, DNA is going to be our primary target of concern. And we knew that ever after the Hershey and Chase experiments, that what we're talking about in terms of long-term effects of radiation exposure is interrupting that genetic signal in some way. And we've talked quite a bit about linear energy transfer, right? So it's a measure of energy transferred into the materials as ionizing particles travel through the materials. And they can be described as low LET, which we said was like X-rays, and we did our little LET dance where we just ionized every now and then, right? It could be moderate LET, which is like a neutron, and we talked about how difficult it is to measure neutron contamination. And then it could be a high LET radiation, so that's things like alpha particles, right, that ionize a whole lot. And the big thing that our textbook adds to this discussion is this will be described in units of kiloelectron volts per micrometer. Kiloelectron volts per micrometer. And so these different types of radiations can be described like the high LET, low LET, or whatever. When we get right down to it, we're talking about how much actual electric potential is it changing or producing as it moves through very, very small areas, right? Like a micron, sometimes it's called, it's very, very small. Okay? So, and then we've already kind of indicated that has a direct connection to how it impacts this target molecule of the DNA, right? Now, as I mentioned before, we could have radiation interact with other parts of the cell and cause problems, right? Like it could, I mentioned how lysomes sometimes are called suicide bags, because if the X-ray or the alpha particle interrupts a lysome and causes it to spill its contents, it could actually eat through the cell, right? It has an acidic content, could actually eat through the cell. But the main thing that we're concerned with radiation biology is not necessarily that. It's more what happens when the X-rays either directly hit the DNA or cause an indirect action through like the radiolysis of water that produces like a free radical that impacts the DNA. Okay? The primary of these two, the primary one that we are concerned with for pretty much everything that we do, except for potentially certain therapeutic applications of radioisotopes and certain nuclear medicine applications, primarily what we're talking about is indirect action. Okay? And the reason why that's the case, even if we're talking about these other applications, is because of, again, the amount of water that we've said is inside the cell. So if I was just looking at the cell and thinking, okay, here's a big target, I'm going to hit this thing, right? But I know that, like, I love that little illustration in the book where it illustrates that like 80 to 85% of the cell is water, so it shows the cell kind of filled up with water. The chances of me hitting water as I interact with that cell in any form of interaction is pretty high, right? And so that's why that's one of the main reasons that we're concerned with this indirect action. So here again is that free radical production, right? I'll blow this up just a little bit. We'll look at this real closely. So if we have, we could potentially have an OH positive or H2O positive, right? So this is a water molecule that's already been ionized. If it's further ionized, it might lose that electron, become a positive water molecule, right? And it could rejoin with another electron without any kind of damage, okay? Or that electron could bond with an OH and produce an OH negative, right? So both of these products will dissociate, though. So both of these products could potentially dissociate. If it's a positive water molecule, the chances are it will dissociate into a positive hydrogen atom, and this should be OH negative here, or OH here, just regular old OH. I don't know why that L is there, right? And if it's a negative water molecule, it could possibly dissociate into OH negative and just a regular old hydrogen atom, right? And, oh, okay, here's that. One represents a free radical. So these two guys out here are free radicals, right? And they're going to knock around. They're going to bump into things. They're highly energized, and they are trying to find stability. And they will do anything they can to get that stability, right? So typically, the OH positive and the OH negative and an H positive will rejoin into just a basic old water molecule without any damage resulting. But this hydroxyl free radical could potentially just go on to create all sorts of damage here, this hydroxyl guy. Or it could also recombine and turn into hydrogen peroxide, which is, as we said, cytotoxic. Right? So this would then indirectly, this chemical process would now affect the DNA, this chemical process that was initially started by a radiation interaction. So we've also talked about, to some degree, this relative biologic effectiveness, the RBE. And so we've said that's a comparison between like a standard radiation dose, and a lot of times the test that they do is a 250 keV X-ray, and then some kind of test radiation dose that will produce the same biologic response. As you can imagine, these tests are really crazy and weird to do, but the easy way to think about it is just it's a dose related to 250 rad divided by the dose of whatever that test radiation was. So, and largely as LET increases, the RBE will increase. The book gives us in box 7.2 a way that like a formula or a problem could be worked like this. So we have a dose in gray from in 250 kilovolts that will produce, like, for example, cataracts or something like that. And then say we have a dose of alpha particles that also produce cataracts. We'll divide those by each other and come up with the relative biologic effectiveness. So in this case, we've said 2 gray of a test radiation produces some kind of biologic reaction. It takes 10 gray of the X-rays to do the same thing. And so when I divide the 10 gray of the X-rays by the 2 gray of the test radiation, I have an RBE of 5 that results. So that means that basically this test radiation is like 5 times the strength of my X-rays. Other kind of physical things, or I guess this is a little bit more tied to a chemical type thing, is we have this oxygen enhancement ratio that also plays a factor in any of these types of radiation biology interactions. So basically this is just saying is that cells are more radiosensitive if they're oxygenated. And I think a large part of this ties back to that radiolysis question, right? If we've got the production of free radicals that are like hydroxyl free radicals, and we've got oxygen also in the cell, like the cell is well oxygenated, well then the chances of it going on to produce a hydrogen peroxide or those free radicals interacting in a way with that oxygen could be increased. But largely, as a rule, cells that are hypoxic can withstand a higher dose. So, but we can also actually come up with what is the oxygen enhancement ratio for a cell, and we just do this by the radiation dose required to cause biologic response without the O2 in a hypoxic condition divided by it with the oxygen present. So we've mentioned that DNA is our target molecule, and it's going to inform our discussion of radiation biology going forward. And so it's important for us to talk about these different types of things that the radiation could either directly or indirectly cause within the DNA. So the DNA could potentially just have an interaction with radiation and repair itself. We could have damage to an actual base. So like the adenine or the thymine could be disrupted or destroyed, and then we lost a base there. We could break a strand of those sugar phosphate chains that form up the DNA ladder. We could break a single strand of it or both strands, and then we could potentially start to cross-link DNA. So let's look at what that looks like here real quickly. So here we have chemical change, right, that I mentioned. We could change potentially that adenine to something else, and so we've got a change in the base there. We could break a single strand of the sugar phosphate chain, or we could break both strands. If this break happens at the same level, that's where we have a potential for a mutation to occur. So when we talk about radiation effects on the chromosomes, any change is considered an aberration, or sometimes it's called a lesion, point mutation, or anomaly. All these terms are interchangeable, right? So aberration, lesion, point mutation, anomaly. And it's important to differentiate between a chromosome aberration versus a chromatid aberration, right? Like I mentioned, that at certain parts of the cell cycle, these interactions are going to be more impactful because it's directly impacted the chromosome, right? Like in the anaphase or that metaphase, we could actually have it destroying both strands of the chromosome. A chromatid type interaction could be something that happens when the DNA is just kind of unspooled, and it could potentially be repaired, but it could also wind up becoming sticky. But chances are it could be repaired. These are some images of plants from outer space, right? So the plant on our left is a normal plant, like before it's been exposed to cosmic radiation, and the plant on the right is the same plant after it's been exposed to a whole lot of cosmic radiation. And you can see in terms of the cellular response or the plant response to the radiation, it didn't like turn into a different kind of plant. It just weakened the plant and started to impactfully change the cell structure itself. So when we're talking about radiation effects on chromosomes, and this is page like 138, 139 in our textbook, we could have an acentric fragment, so like a fragment that just kind of is two broken ends without a centromere, right? So we could have just a fragment hanging out here doing nothing much, right? We could have a dicentric chromatid, right? And this is really weird looking, like it looks something like that, right? All these things can be reproduced, right? Depending on the way it affects, it could be reproduced. If we've got a fragment that has a centromere, it could potentially reconnect with itself and make a ring, right? And the one that we're really, really concerned about are some of these here, where we have translocation, inversion, or deletion processes. And I think one of the things it talks about in our textbook is like, let me see, yeah, covalent cross-links and stuff like that. So translocation would be like, what if we had this this portion of DNA that communicated certain things, right? And we broke this section off, right? And it and it moves to like maybe a different section of DNA and communicates something slightly different. So it comes down here and attaches to this guy, and now it's communicating something it didn't necessarily need to be communicating. Inversion would be the same process if it flipped upside down. Well, what just happened? Sorry, I used the wrong thing, I guess. Well, let's say this guy came down here and reconnected with this DNA, but he flipped around. He flipped around backwards somehow, and now he's created an inversion, right? Another potential thing is that it just deletes it, like it gets rid of it, and all of a sudden the DNA codes for things in the absence of having that information there. So all of these things could potentially lead to now cellular mutation, right? So let's look at some of these slides. Again, as I mentioned earlier, sometimes what we do to evaluate for how this stuff is occurring is we will expose the cells to radiation. We'll wait until they get to something like the anaphase or the metaphase of the cellular reproduction process, where all of those chromosomes have spooled themselves up, and then we'll freeze the cell and we'll look at it underneath a microscope. And we can see, here's some fragments here, like fragments of stuff. Here's a ring. I don't see any dicentric type stuff, but here's that ring here, right, that was reformed. All of this stuff can be So, but nevertheless, if we take a step back from that target theory and think about, okay, other ways that the radiation can interact with the cell, it could actually change the permeability of the cell membrane, right? So it could interact with the cell membrane such that it changes that. It could actually disrupt the cell membrane. It could impact the mitochondria and stop that cell powerhouse from working appropriately. So all of a sudden now the cell doesn't have energy. Or like I mentioned before, it could disrupt a lysosome and cause it to spill that acid out that eats away at the cell. So in terms of thinking about what happens now, so I have this cell, it's exposed to radiation, what next, right? There could be no damage. It could initiate a repair enzyme process and be just fine, right? It could have a division delay or mitotic delay, and this is very interesting because it's almost like the cell knows to hit pause. If it's hit during, like, I think the growth 1 phase or the synthesis phase, it might actually hit pause before it goes into growth 2. And that pause is going to allow it possibly to initiate repair processes. Sorry. It could have interphase death. So we've talked about how G1 and the S phases are very fairly radiosensitive. If the cell's hit with enough radiation during those phases of interphase, it could just die during interphase without it going into any kind of reproduction process. Or we could have reproductive failure, right? And this is a cell that fails to enter into mitosis. It just continues to chug along with what it does. It never reproduces itself. So, changing gears just a little bit, let's talk about the law of Bergonié and Tribondeau from experiments that they did in 1906. So fairly early on, after the discovery of radiation, these guys and one other fellow, I can't remember his name, were doing experiments with, I think, rabbits, and looking at how radiation interacted with different cells within their reproductive systems. So they found that cells are most radiosensitive, and so initially it was thought that these laws only applied to germ cells, but they apply to both germ and somatic cells, these laws. Cells are most radiosensitive when they actively are proliferating, they're highly metabolic, they're undifferentiated, and they're well nourished, right? So actively proliferating, highly metabolic, undifferentiated, and well nourished. Basically when they're stem type cells. So, but to continue on with that, radiosensitivity is a function of metabolic state of the cell receiving the exposure. So the more metabolically active the cell it is, the more radiation could influence it. Radiosensitivity is directly proportional to the reproductive activity and inproportionally to the degree of differentiation. So if we have a cell that's reproducing quite a bit, it's going to be more radiosensitive than, for example, like a nerve cell that does not reproduce itself, right? Some of these, there are exceptions, but that is largely the case. So equal doses of ionizing radiation produce different degrees of damage in different kinds of cells, right? So this just further complexifies the problem for us when we're thinking about radiation dose, radiation exposure is, well, it depends on what cells were hit by this stuff. And the more mature and specialized a cell is, the less sensitive it will be to radiation. Again, I mentioned there are some exceptions to this. The key exception, does anyone know what the key exception is to this rule? It's leukocytes. White blood cells are highly radiosensitive, but they're also highly differentiated. They're kind of the one key exception to the law of Bergonié and Tribondeau. So here is a chart of the radiosensitivity to cells. I think we've seen this once before. But over here we have things that are fairly radio-resistant. On the right side we have things that are fairly radiosensitive, right? So immature sex cells, right? Very radiosensitive. Bone marrow, stem cells, very radiosensitive. The skin, very radiosensitive. We've already talked about how radiation can cause erythema, reddening of the skin, epilation, loss of hair. That's also in the skin, right? Mature bone cells, they're kind of like moderately. All these immature cartilages and mature bone cells are kind of moderately radiosensitive. And adult vessels and cells, right, moderately radiosensitive. Then once we get to things like nerve cells in the brain, we have something that's very radioresistant, right? So it is not going to be as sensitive as some of these other things. And that will be important, especially when we look at different radiation syndromes. All right. So when we're thinking about the effects of ionizing radiation on human cells, we need to first think about what cells we're actually interacted with, right? And probably the one I'll have us focus on the most is the blood stuff, right? So like page 148 through I think 150 in our textbook looks at normal ranges of blood cells as well as the amount of radiation that could cause a depression in those normal ranges, right? So for example, when we're talking about immature blood cells, right? So those bone marrow populations, right? The higher the radiation dose, the greater the severity of the resulting cell depletion. And so that cell depletion will manifest perhaps several weeks after the initial exposure. We might see something like anemia, right? So, let's talk first about these leukocytes, right? I already mentioned the white blood cells, right? So a radiation dose as low as 0.25 gray is sufficient to noticeably depress the number of cells present, leukocytes present in the blood, okay? And they found that doses even lower than that can cause some changes in the leukocytes. So normal white blood cell count is about 5,000 to 10,000, millimeters cubed or something like that. At a dose of 0.25 gray or less, we would expect complete blood cell recovery, right? But we would also expect to see a reduction in the number of leukocytes. It's a fairly radiosensitive thing, even though it's a differentiated cell. So I said it was the one exception to the law of Bergonié and Tribondeau. When we're talking about neutrophils, so this is another kind of white blood cell, they're a little bit more radio-resistant, and so a dose of about twice that, 0.5 gray, will reduce the number of neutrophils. The other kind of big one is thrombocytes, right? Because now we're talking about platelets, and so this could lead to something like anemia. This is very important for us when we're dealing with radiation therapy patients, is that normal ranges for adult blood is about 150,000 to 350,000 cubic millimeters or something like that of blood. Well, we should radiation doses less than 0.5 gray, we could depress that number, and if we depress it too much, right, the patient could become anemic, in addition to potentially becoming more open to infection because we've simultaneously decreased the leukocyte count. So very often in radiation therapy, we are looking at white blood cell counts and red blood cell counts prior to initiating treatment because we don't want to interrupt those counts so much so that the body can't repair and renew itself. So other effects is, as we mentioned, muscle tissue is going to be a little less radiosensitive. Nervous tissue is probably the most radioresistant, unless we're talking about nervous tissue of the embryo fetus. So when we get to any phase of the embryonic development, the nerve tissue could still potentially be damaged by radiation interaction and cause lasting effects to the embryo fetus, versus the exposure to an adult is probably fine. We've mentioned that anytime we're talking about reproductive cells and stuff, again, the law of Bergonié and Tribondeau holds. So if we're talking about immature sex cells, these could be very radioresistant, right? Sorry, the mature sex cells. Is that what I said? Okay, I'm sorry. The immature sex cells, right, could be very, very radiosensitive. So I'll say that again. Immature sex cells, very, very radiosensitive. But once they get to mature sex cells, they're fairly radioresistant. Okay? Sorry about that. All right, well, how do we quantify these different types of cell survivals? The classical way of doing that is to chart it on these curves, right? And so we look at surviving fractions after radiation exposure. So over here we have a surviving fraction tied to a dose of radiation, right? Now what's interesting is that with the low LET radiation, we have a shoulder. With the high LET radiation, we do not have a shoulder, right? The thought is with this low LET radiation, where most of the problems are stemming from indirect interactions with the DNA, the cell has a chance to initiate repair processes as it's being exposed to the radiation, right? So what that results is a shoulder to the curve, right? Which means that this could potentially, we could exploit this in things like radiation therapy to do things like fractionate doses, right, in order to allow for patients to repair between doses. So if we were to fractionate a low LET radiation dose, right, what that would mean is we would initiate the dose and then we would stop the dose, right? And then we would initiate the dose and then stop the dose and initiate the dose and stop the dose. So what that has done is in fractionating the doses now, rather than getting a fall off that looks like this, right, we now have we're exploiting that period of repair that occurs with low LET radiation in terms of cellular survival. So the cellular survival curve will demonstrate the relationship between dose and the percentage of surviving cells. And it's based on experimental data largely that came from Hiroshima. And it suggests that two mechanisms for cell death. There's a lethal single hit. So it's potential that radiation could just damage that chromosome or damage a lysosome, destroy the cell. Or there could be an accumulation of multiple sublethal hits that result in the death of the cell. So we do these really morbid lethality assays where we look at the number of populations that are living after a certain dose of radiation, and we've talked about how we call this the LD50. Another thing that we might talk about is the TD5/5. We use this a lot in radiation therapy, where we say the dose that will cause 5% of the population to have an effect after 5 years. And a lot of times radiation therapy treatments are tied back to that TD5/5 in some way, shape, or form. But if we magnify this up, this is showing us the LD50/30 of a certain dose, right, for human populations. And so this is helpful to look at because what we've said is that there's going to be some kind of threshold, in this case 500 rads, after which we start to see the effects, right? And so as this increases, we have a point where we hit, bam. Now 50% of the population at this point, at this dose, like 350 rad or 3.5 sieverts, will be dead after a month of exposure to this level of radiation. So we'll call that the LD50/30. All right, but there's not just these, as we mentioned, there's not just these physical factors, but let's talk again, just recap real quickly these physical factors that relate to radiation dose. So there's LET and RBE. So the higher the LET and the RBE, these are going lead to an increased fatality number. Okay? I'm sorry. Sorry, that's SF should be surviving fraction. I'm sorry. So higher LET and a higher RBE will lead to a decrease in the surviving fraction. Right? A decrease in the surviving fraction of cells. A higher LET and RBE also result in a steeper shoulder and slope. Right? So the higher that LET is, the higher the steeper that slope will be on our curve. If we're considering dose rates, right? If we use a slower dose rate, if we protract that dose out, right, that could lead to an increase of the surviving fraction of cells. So we call that protraction, or we decrease the dose rate, and it can lead to an increasing surviving fraction of cells. If we slow the dose rates, it can also result in a shallower shoulder and a lower slope of that curve, right? So just extending out, slowing down that dose rate, especially with an acute exposure, could potentially increase the survival rate. With a high LET radiation, it's not affected by changes in dose rate, right? This is just for those low LET radiation exposures. But the high LET stuff doesn't care what your dose rate is. These high LET interactions are packing a serious punch. So this is that graphed out. We've talked about protracted, where we slow down the dose rate. Fractionated, where we're exploiting the fact that there's a repair process, and we're fractionating the dose to allow for a longer time of surviving fraction. Versus an acute dose, this is delivered over a very short period of time. It's not fractionated or protracted. All right, but there's also chemical factors affecting this process, okay? So we've talked a little bit about radiosensitizers, right? These are going to increase the effect of ionizing radiation. And we've mentioned the primary radiosensitizer is oxygen, because anytime there's oxygen present in the cell, it will possibly increase the effects of the radiation. It's not completely understood why this is the case. But as I mentioned before, it's theorized that this is tied to interactions with free radicals. There's also radioresistors, and so there are certain things that we can do potentially to create more resistance to radiation in the body. Sometimes they're called radioprotectants. These are of a lot of interest to the space program because they want to send people into outer space, which there's lots of radiation. So I do have some activities for us.